Alrighty, howdy folks. Got good news. We are moving on to a new chapter, chapter 15. So let's start with section 1, which is about double integrals over rectangles. I'll explain to you what all of that means. Once again, as a motivation, I think let me start with single variable functions. You remember we studied about something called Rayman Sum in Calculus 1. What was the whole idea? The whole idea was if you have a graph of a function y equals f of x, say that curve, and you're supposed to integrate from x equals a to x equals b. Here my x and a and b seem to be 1 and 4, right? You wanted to integrate this. And the Rayman sum says, hey, guess what you can do? You can split this interval a to b, in this case 1 to 4, into different sub-intervals. 1, 2, 3, 4, 5, 6, 7. I seem to have split this into 7 intervals now, right? And make rectangles. Measure the area of each of these rectangles. What's the width is all the same. Okay, each of the rectangles has the same width. So that means that distance 1 to 4 has been divided by 7. 4 minus 1 is 3. 3 over 7 is what we did in order to figure out what the width of each of those rectangles is. Okay, and then the question becomes, what's the height of the rectangle? Well, here Rayman Sum actually gives us a few options. It says for the height, you can use the left end point of the interval. That's what we have done here. What do I mean by that? What I mean by that is, if we look at this first rectangle, the width is exactly the same as the width of any other rectangle. However, when it comes to the height, for that subinterval, look at the left point. That means this x value. Now go up and see what the function's value is at that left end point. Use that as the height of the rectangle. Now you can easily envision another scenario where instead of using the left end points, we could use the right end point. For instance, what's the height of the first rectangle? Well, whatever is the height of whatever is the y value of this point, that point, which happens to be the right end point of that sub interval of that little rectangle. Cool. And there's a third option. We could use the midpoint as the representative of the height of this rectangle. And so on for every other rectangle. Okay. And then one of the things we did, I have details here. We took an interval a to b and split this into n subintervals, and which creates n plus 1 points, x0 through xn. What? Isn't that n points, man? No, x1 through xn would be n points, and we also have a x sub 0, so that actually creates n plus 1 points. Okay. And how do you figure out each of those x sub i's, meaning x sub 0, x sub 1, x sub 2, x sub 3, and so on? Well, you just simply say x sub I is a plus I delta x. And delta x itself is b minus a over n. That's what I was saying here. 4 minus 1 divided by 7. Okay, this is what we did. I don't want to go too much into detail about this one. And after we did that, in Cal 1, we learned that this Rayman sum's limit, the limit of the Rayman sum itself is simply this summation, the sigma I equals 1 to infinity of f of x sub I delta x. Okay. No, I made a mistake. Samuel. This should be sigma I equals 1 to n, and then we take the limit as n approaches infinity. Okay, I'm sorry. Give me half a second and I'll fix that stupid issue. Whoops. Undo. Let me go there, type in n and then delete. Okay, that fixes it. So let me save this and go back to recording. Yep. Limit as n approaches to infinity of sigma I equals 1 to n of this thing. So this itself, just the sum itself is a Rayman sum. And the moment you take the limit of it as n approaches infinity, physically what that means is, imagine splitting this interval into infinite number of rectangles. Then you get the exact area under the curve. And that happens to be the same as the definite integral a to b of f of x dx. Are we cool? All right. Then here is the key. While one way of thinking about this is to say, split this into infinite number of rectangles, right? And then figure out the area of each of those rectangles and add them up to get the area under the curve. This is the concept which you really need to understand. Or you could do something else. You could create one representative rectangle like this, whose width happens to be dx. And where is it located? It's located at some distance x on the x-axis, that rectangle itself. And so what's the height of the rectangle? Well, whatever is the f of x at that point. So you could now, instead of creating all these many rectangles, let's create one representative rectangle at some distance x, whose height would be f of x and width is dx, that infinitesimal length dx. Now, when we say integral a to b f of x dx, what we mean is we will move this rectangle all the way from left at x equals a to x equals b at the right. So first we locate the rectangle all the way at the left, figure out what the area is, scoot it a little bit to the right, figure out the area under of that rectangle, and so on. So as you notice, since the y value is different at different x values, y is a function of x, the height of the rectangle keeps changing as we scoot the rectangle from left to right. It doesn't have to. If the function is constant, that height won't change, but in the event the function y does change with x, the height of the rectangle keeps changing, even though the width of the rectangle is always dx. This is what we say we are integrating along the x direction from a to b. That phrasing you have to become very familiar with, okay? Let me repeat that. In this case, we are integrating along x from a to b. To be more precise, from x equals a to x equals b. This becomes important when we get to the multivariable things. You are integrating along what direction becomes an interesting thing, okay? We'll extend this to multivariable functions. Okay, what do we have here now? There are a few things that are analogous to the 2D counterpart. Okay, so the double integral of f over a rectangle, we had an interval a to b in the previous case. Now we don't have an interval a to b. Instead, we have a rectangle that you could think of as going from x equals a to x equals b, and y equals c to y equals d. I will mention that in just a second. So instead of an interval, we have a rectangle. That's one difference. Okay, and then when we need to find f of xy dA, what exactly we are figuring out? We are figuring out the double integral. This double integral is actually the volume of the solid that lies above the rectangle and below the surface z equals f of xy. That's the key. When we define like this double integral, exactly what are we saying? We are saying, hey, our desire is to find this surface that, what color is that? Tan, some tannish color, brownish color. Okay, so that surface that you see, we want to figure out the volume under that surface over a certain rectangle. That's what we want to find, and this double integral that you see actually does represent that. And the equivalent form of the Rayman sum here is, you go to xij star yij star, which is nothing but some xiyi from xy point, and you okay, yeah, maybe this is better. So here what we are doing is we are picking a point, some arbitrary xy, inside the rectangle, that big rectangle A to B, C to D rectangle. And here we have the dx. Notice this dimension is dx because our x is oriented this way. And dy is this itty bitty piece along this direction is dy because y is oriented that way, right? So we have dx dy, a small area, small rectangle, rectangle. This is equivalent of our just a dx. Instead of just a dx, we have dx and a dy. Instead of an interval, we have instead of a small interval, we have dx dy, the small area, differential area it is. Okay, and we find the volume of this rectangular solid. Again, the question becomes, what's the height of this rectangular solid, man? Well, the height is whatever f of this xy point is. Where is this point located? Well, think of it as in the middle of that itty bitty rectangle, the differential rectangle dx dy. Okay, you could very well pick any other point inside the rectangle to say that's the xy that I want to pick. Okay, and so what's the idea? Well, find the volume of this rectangular solid and do the scooting thing. What do we mean by scooting thing? Well, you want to integrate from x equals a to x equals b. First, if you choose to integrate along x, then do this. Take this rectangle, put it at x equals a. Figure out what the volume of that itty bitty, what should I call it? The rectangular solid, the prism. I like the prism. So figure out the volume of that little prism when this is located at x equals a. Scoot it a little bit, go along in the x direction, scoot it a little bit, figure out what the volume of that prism is, and keep doing that until you get to x equals b. Now go back and scoot in the y direction by just a tad, and and then iterate all the way along the x-axis from x equals a to x equals b. And you would have started with y equals c, though, by the way, x equals a and y equals c. And so scoot along the y each time and go along x and keep repeating that. So when you do that, you get the volume under the surface. That's the whole idea here. All right. So, this is what I was talking about. Suppose that f is a function of two variables that's integrable on the rectangle r equals ab times cd, ab by cd. So x equals a to x equals b and y equals c to y equals d. That's what defines this rectangle. In that case, if your objective is to evaluate this double integral over the rectangle, what that actually means is you would be integrating from a to b and integrating from c to d. Is that cool? Of f of xy dy dx. dy dx is nothing but dA. So what was dA is now we know is dy dx. Is that part clear to you? Here, notice this one has a dA. What in the world is dA, man? Well, that dA is this dx times dy. Okay, and that's what allowed me to replace this dA with dy dx. And what is the integral over r? Integral over r, by virtue of r being a comma b times c comma d, we go from x equals a to x equals b, y equals c to y equals d. Cool. There's one thing that is absolutely essential that you grasp here. How come I didn't say dx dy? I seem to say dy dx. And here is the idea. We should think of this as an inner integral, an inside integral, and an outside integral. So far as this representation is concerned, the inside integral is this c to d integral c to d f of xy dy, just the very first one. So that's the inside integral. Okay, the dy should be, that tells you that we should take the inside integral as integral c to d f of xy dy, which physically means we would integrate along y first, from y equals c to y equals d. And that's why I put this inside the square brackets. So this clearly tells you that you would take this f of xy and integrate with respect to y from y equals c to y equals d. Okay. Then you get some value. Then you integrate along with respect to x from x equals a to x equals b. That's how you evaluate the double integral over a rectangle. Cool. I'll show you quite a few examples to make this concept clear. Integrate along y first. That's what we are saying. And then we will integrate along x. Cool. Which indicates that we first integrate with respect to y from c to d and then with respect to x from a to b. Now, on the other hand, if we were to have dx dy, then we better change this integral, the inside integral, from a to b, because the limits on x happen to be a to b. So here we are indicating that, hey, I want to integrate with respect to x first. So that means my inside integral is with respect to x. So you better use the limits of x for the inside integral, because you are integrating with respect to x. Cool. And then integral c to d for the y equals c to y equals d. All right. Which indicates that we integrate with respect to x first, is all I'm saying. Cool. Next, Fubini's theorem. If f is continuous on the rectangle R, do you know how to read this one? If f is continuous on the rectangle R equals what? Okay. R equals the set of ordered pairs x comma y such that x lies between a and b and y lies between c and d. R is a set of ordered pairs xy such that x lies between a and b and y lies between c and d. Then the theorem says if you are planning to evaluate the double integral over this rectangle of f of xy dA, then whether you integrate with respect to y first or integrate with respect to x first doesn't matter. They are both going to be exactly the same. Right? I'm sure you must have had a question. Hey, how do we decide whether to integrate with respect to x first or y first, man? And Fubini's come here and said, chill. It doesn't matter which way you do. However, of course, caution must be exercised. You better have the right limits. If you are integrating with respect to y, you better have limits on y for the inside integral. Okay, that's the idea. One more thing. Suppose f of xy happens to be separable like this. That means you can write f of xy as some just pure function of x times a pure function of y, and r happens to be this kind of a rectangle. Then you can separate the two integrals. You can separate the x part out and the y part out and integrate them separately and multiply. That's okay to do. Okay, so that's another powerful thing that we'll use. I think I have an example for that one as well. Cool. Let's see. Good. Some simple problems. Integral 0 to 1, integral 0 to 3, x plus y, the quantity square, dx, dy. Can you tell, based on just somebody saying this, we are going to integrate with respect to what first? Yep, we are going to integrate with respect to the inside one, which is dx. So we are going to integrate with respect to x. From what? What are the limits? From x equals 0 to x equals 3. Okay, let's do that. First order of business, let me just multiply this out. I'm sure you must have had a question. Hey, you... Okay, yeah, maybe I can answer it this way. How do we integrate with respect to x? Well, the first term, not a problem. X square. I know that's x cubed over 3 when you integrate. But this one has got a x and y. What do I do about that, man? Right? And that would be, if that's a question you ask, that's a wonderful question. I like such questions. Well, you remember partial derivatives? What did we do when we took partial derivative with respect to x? Well, we thought of y as being a constant. Guess what? Here, when we do this, we are actually thinking of this dx as partial x. I really wish mathematicians actually adopted that symbol, partial x and partial y, as opposed to dx and dy. But somehow they did, and so that's okay. Maybe as a dx and dy as a rectangle, that makes sense. Okay, so but the main point is this. Think of it as partially integrating with respect to x. Think of it. Which means when you are integrating partially with respect to x, think of y as a constant. Armed with that piece of information, this should be easy to integrate. Would you agree? X square, x cubed over 3 is the integral. 2xy, 2 is a constant, y is also a constant, 2y, times the integral of x is x squared over 2. So that makes it 2y times x squared over 2, which reduces to x squared y. Y square, constant, but we are integrating with respect to x, so times x, y square x. And x equals 0 to x equals 3. Right? Those are the limits on x. That's the only thing that you need to pay a little bit attention and keep track of. Okay, so if we plug in, as before, just plug the upper limit minus plug the lower limit. So when we plug the upper limit, we get 3 cubed over 3 is 3 square. 3 square is 9. 3 square is 9, 9y. Y square times 3, 3y square. Cool. And we have this 0 to 1. Now, regular integral, integrate with respect to y and plug the limits. The integral of 9 is 9y. 9y is 9y squared over 2, the integral. 3y squared, the integral is y cube. 3 times y cube over 3, which reduces to y cube. 0 to 1. Plug. And that turns out to be 9 plus 9 half plus 1. Right? 9 times 1 plus 9 times 1 squared over 2. Yeah. Minus 0, 0, 0. Yeah. So that's 29 over 2. Hey, your first double integral. Well, unless you have taken physics. Okay. Integral 0 to 1, integral 0 to 2. Oh, the inside integral is with respect to inside thing is dx. So x equals 0 to x equals 2. And y equals 0 to y equals 1. Right? So integrate with respect to x first, and then plug the limits of x equals 0 to x equals 2, and then integrate with respect to y, plug limit 0 to 1. We are done. Okay, go on, man. Well, when you think about it, could we separate them? Could we make this purely into some function of x times purely a function of y? I don't know. How can you do that, man? It's e to the x minus y. Well, is e to the x minus y the same as e to the x times e to the negative y? Times. It's definitely not. Do not say e to the x minus y is e to the x minus e to the y. No, it's not. E to the x minus y, a to the m plus n is a to the m times a to the n. So e to the x minus y is e to the x times e to the negative y. So we could actually split this as y times e to the negative y and integrate with respect to y times integral 0 to 2 e to the x. But what would have happened had we not recognized that? Absolutely no problems. You could have still done it the old-fashioned way, like the previous problem, and you would get the same answer. Cool? Y e to the negative y dy. Integration by parts? Yep. Turns out that's negative y e to the negative y minus e to the negative y. Apply the limits. Plug check. Integral e to the x, fortunately, is simple. Is e to the x. And so it turns out to be this. Simple? If you think this is simple, I completely agree with you. It is simple. Okay, what about this one? Ooh. I think the book had 0 to 1, 0 to 1 or something like that. I decided to change it to this because the numbers tend to be somewhat better this way. Okay, now you cannot separate into a function of x times some function of y. So we'll have to go with the iterated process. That is, integrate with respect to x. Integrate this guy with respect to x? Man, that looks scary. No, not really. If you had x times square root of x squared plus a square, you would say u equals x squared plus square root of x squared plus a square, u square equals x squared plus a square, and you could have done it like that, right? So that's what I have done. So I said let u be equal to square root of x squared plus y square. U square is x squared plus y square. 2u du equals 2x dx. And there is an x and a dx, so x dx became u du. 2u du is 2x dx. X dx is u du. I made that, all those substitutions. And treat y as a constant, by the way. Right? That goes without saying. And so that integral turns out to be something like this. Now, we need to integrate this from x equals 0 to x equals 4. Maybe I should have made that. Okay. So now let's plug those limits. Plug 4 for x, and you get 1/3 y times 16 plus y square raised to 3 halves, minus plug 0 for x, This becomes 0 plus y square raised to 3 halves. Y square raised to 3 half is y cube. So we have a 1/3 y times 16 plus this guy. Okay. Now we need to, I think in this step I just yanked that 1/3 outside of the integral, and then multiplied that y, distributed the y out, and so we have y times this minus y to the 4. That way, it's easy to integrate y to the 4. So let's take advantage of that. Once again, I did u equals 16 plus y, square root of 16 plus y square, and squared it and differentiated, found the differential, and blah blah. And so we get this. And next, just matter of plugging the limits 0 to 3 for y equals 0 to y equals 3, and that gives us this. Cool. What else? Let's see. Calculate the double integral x times So here they left it to us. 0, the rectangle happens to be 0 pi 6 by 0 pi thirds. So how do we interpret this? We interpret this as x being 0 to pi 6. X equals 0 to x equals pi 6. And y equals 0 to y equals pi thirds. Cool. And so we suitably, when we do this, we better be careful. X sine of x plus y, we have a choice. We can integrate with respect to x first or y first. In this case, I seem to have chosen to integrate with respect to y first because we don't have to apply integration by parts yet. We just have x is a constant. We need to integrate sine of x plus y with respect to y. That is so much easier, right? Negative cosine of x plus y would be the integral of that. So I integrated with respect to y. But when I did that, I absolutely made sure of something. What is that? That the limits would be on the variable y. And y is from 0 to pi thirds. So I made sure that the integral, the inside integral, has the limits 0 to pi thirds. Cool? Integrating with respect to y first. So the limits are y equals 0 to y equals pi thirds. So as long as you're careful about stuff like that, this is pretty piece of cake. Okay. So yeah, cosine, negative cosine of x plus y, and we integrate from y equals 0 to y equals pi thirds. And when you plug those things, you get negative x cosine of x plus pi thirds plus x cosine of x plus 0, just x cosine x. But then, do you remember that formula? Cosine of a plus b, that identity. Cosine of a plus b is cosine a cosine b minus sine a sine b. That's what I did. Cosine x cosine pi thirds minus sine x sine pi thirds. Cosine of pi thirds, cosine 60 degrees, is 1/2. Sine of pi thirds, sine 60 degrees, is square root of 3 over 2. I plug those values here. And then we just have a simple integral in x. However, we could do some simplification here, right? We have a negative 1/2 x cosine x and plus 1 x cosine x. So that makes it 1/2 x cosine x plus 1/2 x cosine x. So I made that simplification. But then here, x cosine x, we have to integrate that by parts. And similarly, x sine x, we have to integrate by parts. I've done that here. And when you do, you get x sine x plus cosine x for the first one, and plug check, folks. And that simplifies to, if this were to be a regular class, doing something, leaving it at this stage, full credit. But I don't know, if you're using stupid WebAssign or something like that, we would have to simplify, I suppose. Is that the last one? Yeah, that's it. So double integrals over rectangles. We will look at what if you don't have just a simple rectangle. Those kinds of situations in the next section. Okay, folks?